From the moment it was first observed, the object that would come to be known as Oumuamua challenged every assumption scientists had about the boundaries of our solar system. Unlike any asteroid or comet previously catalogued, it appeared to arrive from the void between the stars, traveling at a velocity far beyond anything gravitationally bound to the Sun. Its trajectory was hyperbolic, a path that signaled an origin outside our solar system, immediately marking it as an interstellar traveler. Observers noted its sudden appearance, moving with such speed that only a brief window existed to track and analyze its properties before it vanished again into the infinite darkness. Even more astonishing than its course was its shape. Through meticulous analysis of light curves, astronomers inferred an object that could be extremely elongated, possibly hundreds of meters in length, while remaining remarkably narrow. Some models suggested a cigar-like form, others a flattened disk. Its rotation appeared irregular, almost tumbling, creating brightness variations that defied conventional understanding of natural celestial formations. No natural object in our catalogue matched its proportions, and yet there it was, solid and persistent, gliding silently through the solar system with a presence both enigmatic and imposing. As it approached the inner solar system, the lack of any observable cometary tail immediately captured attention. Standard physics dictates that bodies entering the warmth of the sun release gas and dust, forming characteristic plumes that make them unmistakable as active comets. Oumuamua displayed none of these signs. There was no detectable outgassing, no coma, no visible particle trail. And yet, it exhibited a subtle acceleration as it departed the sun, moving faster than predicted purely by gravitational forces. This behavior became the source of intense scientific scrutiny. Each hypothesis, from hydrogen ice sublimation to radiation pressure from sunlight, offered partial explanations but fell short of fully accounting for its mysterious motion. While the world marveled at this unprecedented visitor, a quieter but no less profound revelation emerged. Objects like Oumuamua, traveling interstellar distances, suggest that the universe may be far more populated with wandering debris than previously believed. The implications are staggering. Trillions of small bodies could drift across the galaxy, each a silent witness to the conditions, collisions, and histories of distant star systems. Interstellar space, often imagined as empty and silent, is revealed to be a dynamic environment, filled with travelers that occasionally intersect the orbit of our sun, each carrying a story older than our planet itself. Years later, a second object appeared on the horizon of scientific observation, designated 3I Atelas. At first glance, it seems similar to Oumuamua, an object not gravitationally bound to the sun, moving along a hyperbolic path with an apparent origin far beyond our solar system. Yet, as astronomers observed its trajectory and brightness variations more closely, subtle differences began to emerge, suggesting diversity among interstellar objects. Unlike its predecessor, 3I Atelas exhibited slight but distinct brightness fluctuations, indicative of a surface that reflected sunlight unevenly, hinting at a composition or structure that was unlike the elongated form of Oumuamua. Its velocity, though still extreme by solar system standards, was marginally slower, and its approach appeared to align more closely with the plane of the planets. These nuanced distinctions indicated that while interstellar objects may share the commonality of entering our solar system from distant realms, their forms, behaviors, and physical properties can vary widely. The contrast between these two objects ignited rigorous debate within the scientific community. Could these differences indicate distinct origins, perhaps ejected from entirely separate stellar systems under divergent conditions? Or might they reflect natural variability within interstellar debris shaped over millions or billions of years by gravitational forces, radiation, and collisions in ways we have yet to comprehend fully? In either case, the mere existence of such objects demanded a rethinking of planetary system dynamics and the frequency with which interstellar bodies traverse the spaces between stars. Beyond their physical and orbital characteristics, both Oumuamua and 3I Atlas pose profound philosophical and existential questions. Their silent passage through our solar system underscores humanity's limited perception of the cosmos. While we gaze at the stars, we are only capable of detecting these travelers by chance and with brief observational windows. For civilizations elsewhere, countless such objects may have drifted through their systems, each carrying the potential to reveal history, chemical composition, or even the remnants of technology. If such civilizations ever existed, the possibility that interstellar objects might occasionally serve as natural probes or time capsules challenges our understanding of life, intelligence, and survival on cosmic scales. As telescopes and detection technologies improve, the window to observe and study these interstellar visitors will expand. Advanced survey instruments, equipped with higher sensitivity and broader coverage, will likely uncover many more objects crossing the solar system. Each will offer a unique opportunity to compare properties, test hypotheses about formation and acceleration, and refine models of interstellar dynamics. Observing multiple interstellar objects allows scientists to identify patterns, measure diversity, and gain insight into the composition and evolution of planetary systems far beyond our own. Yet, even as data accumulates, mysteries persist. The precise mechanisms behind the acceleration of Oumuamua remain unresolved. The subtle differences in the brightness and trajectory of 3I Atlas hint at variability that may reflect unknown material properties, structural compositions, or even processes yet unobserved in natural celestial mechanics. These enigmatic characteristics serve as a reminder that the universe still contains phenomena that defy classification, challenging humanity's desire for order and understanding. In contemplating the arrival of these interstellar bodies, it becomes clear that humanity occupies a temporary vantage point within a dynamic galaxy. The frequency and diversity of such visitors suggest that the solar system is not isolated, but is part of a much larger cosmic traffic network where objects have traversed millions of light years. Surviving the harsh environment of interstellar space, each passing object is a messenger from that vast expanse, a witness to events and conditions far older than our own planetary history. Their transit through our vicinity is fleeting, yet their significance endures, compelling us to rethink the nature of space, the origin of matter, and the scope of scientific inquiry. The contrast between Oumuamua and 3I Atlas also provides a crucial opportunity for comparative study. By examining their differences in shape, trajectory, and acceleration, researchers can infer a broader spectrum of interstellar phenomena, moving beyond singular anomalies toward a more nuanced understanding of how objects are ejected from distant star systems, how they survive interstellar travel, and how they interact with the gravitational and radiative forces of the solar system. These insights may reveal not only the mechanics of interstellar object propagation, but also offer indirect clues about the diversity and history of planetary systems throughout the Milky Way. Ultimately, the combined study of Oumuamua and 3I Atlas illustrates the importance of vigilance, observation, and scientific humility. The galaxy is vast, ancient, and full of travelers that do not announce themselves. They arrive without warning, depart without explanation, and challenge assumptions that humanity has long considered foundational. While the data they provide is limited by observation time, their impact on our understanding of the cosmos is profound, expanding the boundaries of what is considered possible and inviting both scientific inquiry and philosophical reflection. The continued monitoring and analysis of these objects hold the promise of revealing secrets about the interstellar medium, the processes that eject material from distant stars, and perhaps even the nature of life and intelligence elsewhere in the universe. In this sense, Oumuamua and 3I Atlas are not merely objects of curiosity. They are guides to the broader cosmic landscape, testaments to the dynamic and interconnected nature of the galaxy, and reminders of the profound mystery that exists just beyond the limits of our knowledge. As the years passed since the passage of Oumuamua, scientists scrutinized every detail, every photon captured by telescopes, searching for patterns and anomalies that might reveal its true nature. Each observation reinforced its uniqueness, while hinting at the possibility that it was not alone. When 3I at LAS appeared, the comparison became inevitable. Astronomers began cataloging its trajectory, composition, and rotation patterns in precise detail, noting subtle distinctions that offered critical insights. Whereas Oumuamua had exhibited extreme elongation and tumbling rotation, 3I at Atelar seemed less elongated but possessed irregular surface reflections that suggested a heterogeneous composition. The brightness variation implied that its structure could be jagged, porous, or fractured. A stark contrast to the smooth, uniform appearance inferred from Oumuamua's light curve. These differences prompted researchers to reconsider the models of interstellar object formation. The diversity implied that multiple processes might generate interstellar travelers. Some could be remnants of planetary collisions, ejected from their host star systems during periods of instability. Others might represent fragments of icy worlds, slowly drifting through the galaxy, shaped over millions of years by cosmic radiation and micro-collisions. The comparison also raised deeper questions. Why do some interstellar objects remain intact while others appear fragile? What forces determine their survival across the vast distances between stars? Each question demanded painstaking modeling, careful observation, and creative scientific reasoning. The disparity in their trajectories offered further insight. Oumuamua had passed nearly perpendicular to the plane of the planets, an unusual entry vector that suggested a violent ejection from its home system, or a rare interstellar path. In contrast, 3I-ATL approached along a trajectory more aligned with the ecliptic, hinting at a different mechanism of origin, or perhaps a common galactic stream influencing its path. This divergence underscored a fundamental truth: interstellar objects are not monolithic. Their origins, histories, and interactions with gravitational fields are as varied as the stars from which they emerge. Researchers also examined acceleration behaviors, which remained a central enigma. Oumuamua's non-gravitational acceleration was dramatic in proportion to its size, while 3I Acteles exhibited subtler yet still unexplained acceleration effects. This suggested that interstellar objects might respond differently to solar radiation pressure or other forces depending on their mass, composition, or orientation. In both cases, the data challenged conventional models, indicating that our understanding of the physics governing small interstellar bodies is incomplete and that the potential for unexpected behaviors must be incorporated into predictive models. The observational campaigns revealed another layer of complexity: rotation. Oumuamua's tumbling rotation produced extreme variations in reflected light, implying that it was rotating chaotically, possibly due to irregular shape or uneven solar radiation effects. In contrast, 3I-ATLAs appeared to rotate more steadily, although its rotation axis and speed were still poorly constrained. These differences in rotational dynamics offer clues to their structural integrity and formation history. Chaotic rotation might suggest collisional fragmentation, whereas steadier rotation could imply a more cohesive structure or a different ejection mechanism. Beyond the physical characteristics, both objects carry profound implications for understanding the frequency and diversity of interstellar bodies. The detection of two such objects within a span of years suggests that the galaxy is teeming with interstellar travelers. The probability of their passage through the inner solar system may be far higher than initially assumed, compelling astronomers to refine models of stellar system dynamics, interstellar object density, and the likelihood of similar encounters in the future. This realization reshapes how humanity perceives the solar system, not as an isolated collection of planets orbiting a single star, but as a waypoint in a vast, flowing cosmic network where objects drift across light years and occasionally intersect our path. The differences between Oumuamua and 3I Atla also influence considerations about potential extraterrestrial activity. While natural explanations remain most probable, the distinct characteristics and behaviors of these objects leave open the possibility, however remote, that advanced civilizations elsewhere could inadvertently or deliberately place interstellar objects on specific trajectories. This idea is approached with caution by the scientific community, yet it serves as a reminder of the vast unknowns of interstellar space. Even if both objects are purely natural, their study provides an unparalleled opportunity to understand processes in distant planetary systems that cannot otherwise be observed. Furthermore, the study of these objects highlights the limitations of human observational capacity. Both Oumuamua and 3I Atlas were discovered only because of dedicated, wide-field surveys with sufficient sensitivity to detect fast-moving, faint bodies. The detection windows were brief, leaving little time to gather comprehensive data. These constraints reinforce the importance of expanding observational networks, deploying faster detection algorithms, and preparing rapid response observation strategies. With more frequent and detailed observations, astronomers hope to identify patterns in the composition, trajectories, and behavior of interstellar objects, gradually unveiling the hidden dynamics of the galaxy. In addition to their scientific significance, these interstellar visitors have captured the public imagination. The contrast between Oumuamua's eerie, elongated form and 3I Atlas's subtler, irregular presence illustrates the vast spectrum of possibilities that exist beyond our solar system. Media coverage and academic discussions alike emphasize not only the rarity of such events, but also their philosophical weight. Humanity is reminded of its vulnerability, of the transient nature of observation, and of the necessity to remain intellectually humble in the face of phenomena that exceed current understanding. Finally, the combined analysis of these two objects establishes a foundation for future research. By comparing and contrasting their physical properties, orbital dynamics, and observed behaviors, scientists are beginning to construct a taxonomy of interstellar objects. This emerging framework may eventually allow predictions about the frequency, size distribution, composition, and potential origins of interstellar bodies, laying the groundwork for systematic exploration and study. Each new discovery, while unique, will be contextualized within this framework, gradually transforming interstellar phenomena from isolated curiosities into a coherent field of scientific inquiry. The arrival of Oumuamua and 3I Atlas serves as a cosmic lesson in variability, resilience, and mystery. One object elongated and tumbling, the other irregular and subtly accelerating. Together they underscore the incredible diversity of material that exists between stars, challenge the assumptions of celestial mechanics, and remind us that even in the vast silence of space, surprises abound. As humanity prepares for future interstellar visitors, the knowledge gained from these two objects will guide our expectations, inform our technology, and inspire generations to look upward with a combination of curiosity, caution, and wonder. Beyond their individual characteristics, Oumuamua and 3I Atlas offer a window into the broader architecture of the galaxy. They are not isolated anomalies. They are fragments of an interstellar ecosystem, each shaped by the gravitational, radiative, and collisional forces that govern the Milky Way. Consider the journey of such an object, ejected from a planetary system millions or billions of years ago, traveling through the void where cosmic rays slowly alter its surface, colliding with micrometeoroids, surviving the tidal forces of nearby stars, and finally arriving at a star system unlike its origin. The probability of survival through such conditions underscores not only their resilience but also the extraordinary precision of the natural forces that allow them to endure. The contrast between Oumuamua and 3I Atlas is particularly instructive in this regard. Oumuamua's elongated shape and tumbling motion suggest a history of violent ejection, possibly from close encounters with massive planets or the remnants of collisional disruption. Its surface appears remarkably intact despite these stresses, indicating a dense composition capable of withstanding millennia in interstellar space. Conversely, 3I-IATLs, with its irregular surface and subtle rotational characteristics, hints at a less dramatic, perhaps more gradual journey, possibly ejected under different gravitational circumstances or originating from a less dense or fractured parent body. These distinctions illuminate the variety of pathways by which interstellar objects traverse the galaxy and reveal that no single model can encompass the full spectrum of possibilities. The trajectories of these objects also carry profound implications for understanding stellar dynamics. Hyperbolic paths, such as those exhibited by Oumuamua and 3I Atlas, require velocities exceeding the escape velocity of the solar system, suggesting that ejection from their home systems was both energetic and precise. Mapping such trajectories backward can hint at their potential origin regions within the galaxy, offering a tantalizing, albeit incomplete, glimpse into the architecture of distant planetary systems. Even in the absence of exact identification, these trajectories provide valuable constraints on stellar interactions, the mechanics of planetary ejections, and the broader flows of matter across interstellar space. Acceleration behavior adds another layer of mystery. While Oumuamua exhibited pronounced non-gravitational acceleration without detectable outgassing, 3I Atla showed subtler deviations. These differences indicate that interstellar objects respond differently to environmental factors, potentially depending on surface properties, structural composition, or interaction with solar radiation. The possibility that radiation pressure or micro-outgassing could influence such objects challenges the classical assumptions of celestial mechanics and underscores the need for continuous refinement of astrophysical models. Each measurement, each subtle deviation, enriches our understanding of the physical laws governing small bodies and extreme conditions. The study of these visitors also opens philosophical and existential avenues. Humanity often conceptualizes the cosmos as vast but static, with celestial bodies following predictable orbits. The passage of interstellar objects, however, introduces dynamism, unpredictability, and a profound reminder of our temporal and spatial vulnerability. Observing Oumuamua and 3I Atlas invites reflection on the scales of time, distance, and survival. These objects predate the Earth, traversing space before the first multicellular life existed and will continue long after humanity is gone. They are cosmic travelers that embody persistence and continuity in a universe defined by change. Another area of exploration is the potential chemical and structural diversity of these objects. Spectroscopic analysis, albeit limited by observational constraints, suggests that interstellar objects may harbor compositions unlike any found in the solar system. Differences in albedo, reflection spectra, and surface textures indicate that each object carries information about its system of origin, the types of stars, planetary bodies, and formation environments that contributed to its creation. Oumuamua and 3I Atlas, while superficially similar, exemplify this diversity, emphasizing that each interstellar object is a natural archive of conditions far beyond our immediate reach. The implications extend to considerations of potential life, habitability, and panspermia. Interstellar objects may transport organic compounds, volatile materials, or even microscopic life forms between star systems, though such possibilities remain speculative. By analyzing the composition and trajectory of bodies like Oumuamua and 3I Atlas, scientists can better constrain models of interstellar material exchange and its role in the chemical evolution of planetary systems. These insights bridge the disciplines of astrophysics, astrobiology, and planetary science, offering a holistic view of how matter travels and transforms on galactic scales. Moreover, the presence of multiple interstellar objects provides a rare opportunity for comparative study. By examining the similarities and differences between Oumuamua and 3I Atlas, researchers can begin to construct probabilistic models of interstellar populations, estimating frequency, size distribution, composition, and potential survival rates. Such models not only inform observational strategies but also provide predictive power, enabling astronomers to anticipate future interstellar visitors and prepare rapid response observation campaigns to capture fleeting data before these objects vanish beyond detection. From a human perspective, these discoveries demand both humility and curiosity. They remind us that even in our most advanced era of observation, the galaxy holds surprises that are sudden, unannounced, and profoundly informative. Each interstellar object that enters the solar system challenges our assumptions about the limits of physics, the diversity of planetary systems, and the scale of cosmic time. They are both teachers and enigmas, emphasizing that knowledge is incremental and that every observation can fundamentally reshape our understanding of the universe. Finally, the combined study of Oumuamua and Astroids points toward a future in which humanity becomes increasingly attuned to interstellar phenomena. As survey technologies improve and computational models become more sophisticated, the detection, tracking, and analysis of such objects will grow more precise, transforming fleeting observations into comprehensive scientific narratives. These interstellar travelers, once rare curiosities, are poised to become key informants about the structure, dynamics, and evolution of the galaxy, bridging gaps in our knowledge and inspiring generations of inquiry, reflection, and exploration. In this way, the passage of these two extraordinary visitors serves not only as a testament to the richness and unpredictability of the cosmos, but also as a profound invitation to observe carefully, to think deeply, and to recognize that even the smallest objects traversing the void can carry the weight of galactic history, cosmic mystery, and the promise of discovery yet to come. Looking forward, the passage of Oumuamua and Astroids signals a new era in astronomy, one in which humanity must anticipate and prepare for interstellar visitors as regular phenomena rather than rare anomalies. Astronomers recognize that these objects are not solitary events. The galaxy likely contains billions of fragments drifting silently between stars, each carrying clues about its system of origin. Detecting them requires not only powerful telescopes, but sophisticated algorithms capable of scanning the sky in real time, discerning faint, fast-moving bodies against the dense backdrop of stars. Advances such as the Rubin Observatory, with its unprecedented survey speed and sensitivity, promise to increase detection rates and allow for longer observation windows, providing more detailed measurements of trajectory, brightness, and spectral characteristics. Equally important is the refinement of computational models. Each interstellar object adds to the collective dataset, enabling scientists to simulate galactic dynamics with greater accuracy. By analyzing trajectories, velocities, and accelerations, researchers can begin to map the probable origins of these visitors, reconstructing the forces and events that ejected them from their home systems. In turn, this offers a glimpse into the formation and evolution of distant planetary systems, their stability, and the processes that produce interstellar debris. With every new detection, a mosaic of the galaxy's activity slowly emerges, revealing not only the diversity of interstellar objects, but also the interconnectedness of planetary systems across light years. Technological innovation is also central to the future study of these phenomena. Observing fleeting interstellar visitors demands instruments that are rapid, precise, and capable of multi-wavelength detection. Advances in spectroscopy, photometry, and high-speed imaging allow scientists to extract chemical and physical data even from dim, fast-moving objects. Potential missions to intercept or closely study interstellar bodies are being proposed, ranging from rapid response flybys to spacecraft capable of rendezvous with such visitors. Such missions, if realized, would mark a new frontier in space exploration, turning momentary observations into direct physical sampling, revealing surface composition, internal structure, and potential organic material. The implications of these discoveries extend beyond science into philosophy, culture, and humanity's conception of its place in the universe. Objects like Oumuamua and 3i and AS remind us that the cosmos is vast, dynamic and indifferent to our observation schedules. They arrive unannounced, follow paths dictated by forces both familiar and subtle, and depart, leaving only questions and traces of light. Yet in this unpredictability lies opportunity, the chance to expand our understanding, to connect our solar system to a broader galactic context, and to embrace the notion that life, matter, and history exist far beyond the confines of Earth. There is also a profound lesson in patience and preparedness. Interstellar objects pass swiftly, their observation windows measured in days or weeks, yet the knowledge they carry persists. Humanity must cultivate vigilance, develop international collaboration, and maintain instruments capable of continuous sky monitoring. The frequency of these events suggests that future generations will witness dozens, perhaps hundreds of such visitors, each revealing unique aspects of the galaxy's hidden activity. The ability to study them in detail would define a new era of discovery, one in which fleeting celestial travelers become touchstones for understanding the larger cosmic web. Moreover, the diversity between Oumuamua and 3i Atlas underlines the need to expect the unexpected. Not all interstellar objects will resemble their predecessors. Some may be icy, others metallic, some elongated, others spherical. Some may harbor complex organic molecules, while others are inert rock. This variability challenges researchers to remain flexible, creative, and open-minded, emphasizing the importance of comprehensive observation strategies that can accommodate a range of possibilities. Each object, regardless of its characteristics, contributes a piece to the puzzle of galactic evolution, and no detail can be dismissed. At the same time, these interstellar travelers inspire broader contemplation. They serve as reminders of the galaxy's immensity and our own small but perceptive vantage point within it. By observing them, humans engage in a form of cosmic archaeology, piecing together histories that span millions of years and light-years of distance. In their silent journey, Oumuamua and 3i communicate through physics rather than words, conveying information about forces, collisions, compositions, and trajectories. Every photon reflected from their surfaces is a message from the distant past, and every deviation from predicted motion is a clue about processes occurring across the galaxy. The next step in this unfolding story may involve not only observation but interaction. The concept of sending spacecraft to intercept interstellar objects, though technically challenging, is increasingly plausible. Missions capable of rendezvous could capture data directly, analyzing isotopic ratios, mineral compositions, and surface structures in unprecedented detail. Such missions would transform interstellar visitors from transient phenomena into tangible objects of study, turning the fleeting into the permanent and revealing the most intimate details of cosmic history. Finally, the passage of these two objects illustrates a profound narrative about human curiosity, resilience, and the pursuit of understanding. From the first detection of Oumuamua to the subsequent arrival of 3i Atlas, humanity has been forced to confront both the limitations and the potential of scientific inquiry. Observers, theorists, and engineers alike have grappled with the unknown, constructing models, refining instruments, and challenging assumptions. The process itself reflects a fundamental truth. Exploration is as much about expanding the mind as it is about observing the universe. In the quiet trajectories of these interstellar travelers, we find a mirror to our own desire to reach beyond, to understand, and to connect with the cosmos in ways that are both tangible and profound. Through the lens of Oumuamua and 3i Atlas, the galaxy becomes a living laboratory, a dynamic network of matter, energy, and history. Each visitor is a teacher, a messenger, and a testament to the incredible diversity of interstellar phenomena. By studying them carefully, humanity is learning not only about distant star systems, but also about our own capacity for observation, analysis, and awe. These objects remind us that the universe is filled with surprises, that every journey across the void carries a story, and that we are only beginning to comprehend the vast, interconnected web of matter and motion that defines our galaxy. In the end, Oumuamua and Three-Eye Atellus are not merely celestial anomalies. They are chapters in a larger story, one of interstellar movement, cosmic diversity, and the relentless drive of humans to understand what lies beyond. Their silent passage offers knowledge, wonder, and a profound reminder that the universe is far more complex, dynamic, and fascinating than even our most advanced science can yet fully explain. As the stories of Oumuamua and Three-Eye Atellus unfold, it becomes increasingly clear that these interstellar travelers are more than fleeting curiosities. They are keys to understanding the galaxy itself. Their trajectories, compositions, and behaviors do not merely inform us about individual objects. They hint at a vast interconnected network of material flowing between star systems. Each object, unique in shape, size, or acceleration, represents a fragment of cosmic history, a messenger from distant worlds that predates the formation of our solar system. Comparing the two objects reveals a spectrum of interstellar diversity. Oumuamua, elongated, tumbling, and enigmatic, embodies the dramatic high-energy processes that can eject matter from planetary systems. Three-Eye Atellus, irregular and subtly accelerating, illustrates the quieter, perhaps more common pathways through which material can drift between stars. Together, they show that interstellar space is not uniform, that objects are not homogeneous, and that the forces shaping them vary with origin, history, and environment. By studying their differences, scientists can infer not only physical characteristics, but also the galactic processes that govern formation, ejection, and survival of interstellar bodies. These comparative insights have profound scientific implications. Mapping the trajectories backward, while fraught with uncertainty, allows researchers to hypothesize potential origin regions, linking observable data to distant stellar neighborhoods. The contrasts in rotation, brightness variation, and acceleration suggest variations in composition and structure that challenge existing astrophysical models. They force the development of new theories regarding interstellar object dynamics, material strength, and radiation response, pushing the boundaries of planetary science and celestial mechanics. The broader significance extends to the frequency of interstellar visitors. With two such objects detected within a relatively short time frame, statistical models suggest that the solar system may be traversed regularly by objects from other stars, previously invisible due to technological limitations. This realization reframes our understanding of the galaxy not as a static backdrop, but as a dynamic, interconnected environment in which matter moves continuously across immense distances, occasionally intersecting with our planetary system. The philosophical resonance of these findings is equally profound. Observing objects that have traveled millions of light years before entering our solar system reminds humanity of its small but perceptive vantage point within the galaxy. Each photon reflected from these bodies carries information about distant epochs and stellar processes, connecting observers on Earth to histories and environments that are otherwise inaccessible. In contemplating these objects, humans are invited to consider not only the mechanics of space, but also their place in the cosmic narrative, of fleeting species glimpsing the movements of matter across incomprehensible scales. Furthermore, the study of Oumuamua and Three-Eye Atellus emphasizes the importance of vigilance, preparedness, and collaboration. Detecting interstellar objects is inherently challenging. Their small size, faintness, and high velocities demand rapid response observation, international cooperation, and continual improvement of technology. Future missions may involve intercepts, flybys, or even sample returns, transforming ephemeral sightings into detailed analysis. Each discovery not only enriches knowledge, but also builds the foundation for systematic exploration of interstellar matter. preparing humanity for a future in which such encounters become routine rather than extraordinary. The differences between the two objects also hint at the potential for unexpected surprises in the interstellar population. Not all will resemble the known examples. Some may be icy, metallic, or covered with volatile compounds. Some may carry organic material, perhaps hinting at chemical processes relevant to the origin of life. The diversity of these bodies encourages an approach that is both scientific and imaginative, blending empirical observation with creative theorizing to anticipate what may arrive next. Ultimately, the passage of Oumuamua and Three-Eye Atlas teaches a profound lesson about the nature of discovery. Each object, silent and ephemeral, serves as a messenger from a galaxy that is active, ancient, and far more complex than early astronomers imagined. They challenge assumptions, expand scientific horizons, and inspire reflection on the interconnectedness of the cosmos. By observing, analyzing, and comparing them, humanity gains insight not only into distant planetary systems, but also into the very processes that shape matter and life across the Milky Way. In conclusion, these interstellar travelers exemplify both the rigor and wonder of scientific inquiry. They are simultaneously objects of study and symbols of cosmic scale, bridging the gap between observation and imagination. As telescopes become more powerful, computational models more refined, and humanity more attuned to the subtle signals of the galaxy, the knowledge gleaned from Oumuamua and Three-Eye Atlas will illuminate paths to understanding other worlds, the forces that govern them, and the history of matter in motion across the vast expanse of space. Their silent journeys are a testament to the richness of the universe, the diversity of its processes, and the enduring curiosity that drives humans to explore, comprehend, and marvel. Through these interstellar objects, we begin to see the galaxy as a living, flowing system, a network of matter and energy in perpetual motion. Every new visitor provides data, context, and perspective, slowly revealing the vast narrative of the cosmos. Oumuamua and Three-Eye Atlas, in their similarities and differences, have inaugurated a new chapter in human understanding. A chapter in which interstellar phenomena are not anomalies, but integral elements of a dynamic, astonishing universe. Awaiting further observation, study, and wonder, the passage of both Oumuamua and Three-Eye Atlas compels us to see interstellar objects not as rare anomalies but as a continuous phenomenon, a river of matter flowing silently across the galaxy. Their distinct appearances and behaviors, one elongated and tumbling, the other irregular and subtly accelerating, illustrate the profound diversity of these cosmic travelers. Each carry a unique history written over millions or billions of years. They challenge the assumption that interstellar objects must conform to patterns observed within our solar system, demonstrating that the galaxy is far more dynamic, complex, and unpredictable than previously imagined. Comparing the two, scientists can begin to trace the invisible fingerprints of their origins. Oumuamua's extreme elongation and chaotic rotation suggest a violent ejection from a distant planetary system, perhaps the remnant of a collision between massive bodies. Three-Eye Atlas, with its irregular shape and steadier rotation, points to a different formation or ejection mechanism, hinting that multiple pathways exist for material to escape the gravitational grip of stars. These contrasts allow astronomers to build a richer taxonomy of interstellar matter, to predict behaviors, and to model the variety of processes that send objects hurtling through interstellar space. Their trajectories reveal not only paths through our solar system, but also clues about galactic dynamics. Hyperbolic orbits, varying approaches, and subtle deviations from expected acceleration suggest that the Milky Way is a network of forces, gravitational tugs, radiation pressure, and stellar perturbations that guide these objects across unimaginable distances. Each passing body, therefore, acts as a probe, recording the interactions of matter with stars, planets, and interstellar environments long before humans had the capacity to observe. The philosophical and existential implications of these travelers are equally profound. They remind humanity that the cosmos operates on scales of time, distance, and energy far beyond our perception. These objects predate the Earth, traversing the galaxy silently, unaffected by human observation, yet offering lessons that connect us to the broader universe. They encourage a humbling perspective, one that recognizes our fleeting tenure and limited scope, while simultaneously inspiring curiosity, imagination, and the pursuit of knowledge. Moreover, the detection of multiple interstellar objects hints at a galaxy teeming with unseen wanderers. If two have been observed within a span of years, statistical models imply that thousands more traverse the Milky Way, invisible to us until they intersect our observational capacity. This realization transforms the way we perceive our solar system, no longer an isolated pocket of matter, but a waypoint through which interstellar travelers regularly pass. Each encounter is a fleeting window into distant worlds and stellar histories, an opportunity to collect knowledge otherwise impossible to obtain. The study of their composition, light reflection and rotation provides insights into the diversity of matter in the galaxy. Differences in albedo, acceleration, and shape indicate a range of structural integrity, chemical makeup, and surface processes. Some interstellar objects may be dense and solid, others porous or fractured, some icy, some rocky. Each characteristic tells a story of formation, survival, and journey through interstellar space, revealing processes that shape planetary systems far beyond the reach of direct observation. The existence of such variability emphasizes the need for vigilance, rapid observation, and international collaboration. Telescopes must scan the sky continuously, algorithms must detect fleeting movement, and rapid response missions may one day be deployed to study or even intercept these bodies. The technological and scientific infrastructure built around interstellar object detection represents a new frontier in astronomy, one where fleeting encounters can yield insights into the structure and evolution of the galaxy. Finally, the combined study of Oumuamua and 3I allies lays the foundation for understanding interstellar matter as a whole. By comparing their differences and similarities, astronomers begin to define a framework that can categorize and predict future objects, offering a roadmap for systematic exploration. They are teachers, messengers, and records of distant worlds, bringing both scientific data and philosophical reflection to those willing to observe and interpret them. Their passage is both fleeting and eternal, a testament to the galaxy's vast complexity and the human pursuit of understanding. In observing them, humanity learns that the universe is not static, that matter moves, evolves, and carries stories across unimaginable distances. Oumuamua and 3I are not merely objects, they are symbols of discovery, diversity, and cosmic connection, inviting us to look beyond our solar system, to imagine the forces that shape distant worlds, and to contemplate our place in the vast flowing network of the Milky Way. Beyond the individual characteristics of Oumuamua and 3I, their existence points to a vast population of interstellar objects that silently drift across the galaxy. Each carries a story shaped by its system of origin, the violent or gentle forces that ejected it, and the billions of years spent traveling the void. These travelers are more than curiosities. They are fragments of planetary evolution elsewhere, natural probes that traverse distances beyond imagination, arriving in our solar system by chance, but offering insights into galactic history, planetary formation, and the mechanics of stars and planets across light years. The discovery of these two objects has prompted a re-evaluation of the Milky Way as a dynamic system, not a static collection of stars. Matter flows continuously, connecting stellar neighborhoods through collisions, ejections, and gravitational interactions. Understanding this interstellar network requires careful mapping of object trajectories, velocity vectors, and acceleration patterns, revealing the invisible forces at play. Oumuamua's tumbling and acceleration contrasted with 3I subtler deviations. suggest that interstellar objects can have widely varying interactions with the solar system's gravitational field, solar radiation, and cosmic environment, providing a laboratory to study physics on scales unreachable by Earth-bound experiments. Observational technology is now adapting to this reality. Wide-field surveys, high-sensitivity telescopes, and automated detection algorithms are being deployed to capture fleeting interstellar visitors in real time. Each observation is a race against time. These objects move rapidly, often detectable for only days or weeks. The ability to gather spectral data, brightness curves, and rotational information in such brief windows is a testament to human ingenuity, and it provides unprecedented opportunities to infer the composition, structure, and history of distant planetary material without ever leaving Earth. These discoveries also hint at the probability of more exotic material crossing the galaxy. While Oumuamua and 3I Atalays may be rocky or metallic, others could carry ices, organics, or even compounds relevant to the origins of life. Each new detection expands the known diversity of interstellar matter, challenging models of planetary formation and ejection, while offering clues about the prevalence of certain chemical environments in the galaxy. Scientists are beginning to ask whether the movement of matter between stars could contribute to panspermia, the distribution of life's building blocks, or the chemical evolution of planetary systems. From a human perspective, these objects are also mirrors of our curiosity and ingenuity. Detecting, tracking, and analyzing such fleeting visitors demands global cooperation, technological sophistication, and rapid mobilization of observational resources. Humanity's ability to perceive these small, fast-moving interstellar travelers is a remarkable achievement, reflecting both the limits and the potential of our species in understanding the cosmos. The fleeting nature of these encounters adds urgency and drama, highlighting the tension between the vastness of the galaxy and the narrow window of opportunity for observation. Furthermore, studying the differences between Oumuamua and 3I Atalays offers a roadmap for future exploration. By comparing shapes, reflective properties, rotational behavior, and acceleration patterns, scientists can begin to classify interstellar objects into categories. Constructing predictive frameworks for detection and analysis, each new discovery refines these frameworks, informing telescope design, observational protocols, and even potential spacecraft missions aimed at intercepting or sampling such objects. In this sense, these travelers are both subjects of study and teachers, guiding humanity's approach to the galaxy at large. The philosophical implications are equally profound. The Milky Way is not merely a backdrop for human observation. It is alive with movement, energy, and matter, with objects silently carrying the history of distant systems across unimaginable distances. Each encounter reminds observers of the impermanence of life, the vast scale of cosmic time, and the resilience of matter itself. Oumuamua and 3I Atalays, in their silence and speed, confront humans with the reality that the universe operates on scales far beyond human perception, yet can still be understood through careful observation, reasoning, and imagination. Finally, the interplay between scientific observation and human wonder cannot be overstated. The arrival of these interstellar objects demonstrates that knowledge is both cumulative and serendipitous. A single detection can spark decades of research, inspire technological innovation, and reshape our understanding of the galaxy. They are reminders that the universe is not fixed or predictable, that matter moves continuously across the void, and that each passing traveler carries information essential for piecing together the larger story of the Milky Way. Through the lens of Oumuamua and 3I Atalays, humanity glimpses a universe alive with motion, rich with diversity, and full of surprises. They challenge expectations, reveal new phenomena, and invite both scientific inquiry and philosophical reflection. As technology improves and observation networks expand, these fleeting visitors will continue to illuminate the hidden dynamics of interstellar space, encouraging a deeper understanding of the galaxy, the origins of planetary systems, and humanity's place in the vast cosmic web.